In this video, I introduce automatic data curation for self-supervised learning. Vision foundation models are pre-trained in a self-supervised manner on curated data that requires extensive human effort. However, the large diversity and balanced datasets are costly and time-consuming. Hierarchical k-means clustering curation is applied to generate balanced datasets for vision foundation models to achieve high performance across broad domains. As shown here, this imbalanced dataset with a long tail. Hierarchical k-means use the original data as input to generate a uniform distribution of centroids. And then hierarchical sampling in the top to a down way to generate the balanced data set that is used to train the self-supervised learning model. Data balance having roughly the same number of the data points per data type is an important factor for self-supervised learning. For example, unbalanced data set alpha larger than 0 results in worse accuracy in linear classification on ImageNet, as shown here. This alpha value and this corresponding accuracy. K-means clustering is used to find coherent structures in data, which divides data into groups, such as data points in the same group are close to each other, according to specific distance in embedding space. While those in different groups are far away, let xi is the embedding of a data point I, keys number of clusters. And MIG is the binary membership variable indicating if data point I belongs to the cluster key. The k-means aims to find MIG that minimizes the total intra-cluster distortion, as shown here and explained in this figure, where CG is the centroid of cluster G and D is the squared L2 distance. Hierarchical k-means approximate the uncurated raw data as a uniform distribution U over support of data distribution P, as shown here. The centroids of k-means clusters follow a distribution Q with an normalized density P, as shown here, which stays close to the data distribution P in high dimension. Q moves closer to U than to the data distribution P, as shown here. Q moves closer to the distribution U, and then by this way, Q approximates the data distribution P. The first k-means is computed on the raw data, as shown here. This raw data, this first k-means. The T's k-means groups the set C, T minus 1 of the centroids of T minus 1's k-means into KT clusters, as shown here in this between this level T, this level 1. The centroids of final k-means follow the distribution with a normalized density P, which converges to U when T tends to infinity. The centroids of hierarchical k-means in the level T distribute uniformly over the data support. Automatic curation technique can build a balanced dataset of the data pool by uniformly sampling a fixed number of data points from corresponding subtrees of the centroid. With a small subtrees with fewer leaves than needed, the automatic curation technique takes all the leaves without oversampling, as shown here, for example. The training data sampling is through the tree in a top-down way, as shown here. This top, this down in this way. Give the number of points to sample from a subtree of a level T, as shown here. The number of points is sampled from his own subtrees with binary search. And this process is repeated down to the level 1, step by step from here to here. Once getting these numbers for cluster in level 1, as shown here, the hierarchical sampling can sample them to form the balanced subset for self-supervised learning, this uniform distribution. For more details, please check with these references. Thank you. Bye.